Okay, so we are going to proceed with our work on the PIV. Okay, so let us look at it. So in the PIV, as we know that we have talked about the seeding and all other things, now let us look at the lasers. Okay, so now that in the we have it in the PIV, now let us look at how the lasers can actually how would they affect the PIV. So what you see over here is a schematic of the laser. Okay. So what does a laser actually do is basically it consists of atomic or molecular gas or semiconductor or solid material. Okay. And then you have a pump source. We already have talked a little bit about the laser. It excites the laser material by introduction of electromagnetic or chemical energy. Now there is a mirror arrangement, which basically is a resonator, which allows oscillation within the laser material and therefore helps us to populate a particular mode. Okay, so this is the schematic of the laser that we have already familiar with, right? So remember that it can be gas, it can be semiconductor, it can be solid material also. Now, let us look at the how does lasing happens. We already talked about it in our laser presentation. Let me just quickly go through it one more time. So this is the typical Einstein's two-level diagram in which there is a lower energy level and there is a higher energy level. So when incident photon of a particular wavelength or color impinges on this energy level, what it can do is that what you can do is that there are a large number of so what happens is that this photon now interacts with this electron, and this electron is now promoted. It absorbs the energy and gets promoted to a higher energy level after some time, which is tau. So this is called absorption, where the difference in energy is actually matches with the color of the photon. Now there can be spontaneous emission also. This electron will go down to the ground level and emit a photon after some time. And then there is stimulated emission. So that means there is an electron already in the excited state. You basically bombard it with a photon, and you basically get two photons coming out of it, which are actually which are coherent, they're phase locked. For large number of atoms, like one of the two processes, absorption or stimulated emission predominates. In case of population inversion, that is N2 greater than N1. Normally your N1 will be greater than N2 under thermal equilibrium. So as we can see that, just a second, let me just lower this thing. Okay. So you can see that however, in a system where there are only two energy states, as we described, the population inversion cannot be achieved because the number of atoms in N2 in level E2 equals to the number N1 in level E1. So therefore, what will happen, absorption and stimulated emissions will be equally likely, and the material will become transparent at the frequency, which is E2 minus E1 divided by H. However, if we introduce a three-level system, which is right around over here, this is also not very efficient. What a three-level system does is that there is a metastable state, which is E2 over here. So E3 is the upper energy level where the electrons are pumped. And then you have a metastable upper laser level where the electrons from E3 undergoes non-radiative transition and comes to this state, and then they actually come back to the ground state, and this is what the laser action happens. So laser action happens between E2 and E1. But what happens here, because a fraction of more than 50% of the atoms has to be excited in order to amplify an impinging photon. This means that the energy that is needed for this excitation is lost for the amplification. So in this case, what people do, we go to a 4-level laser system in which the lowest level, which is E2, does not coincide with this. So you see the lasing actually happens between E3 and E2. Okay. So in this way, it is easier to achieve a population inversion, and a 4-level laser system requires substantially less pumping power. So therefore, you pump it to E4, then there is a first non-radiative transition, then there is a lasing transition, and then there is another non-radiative transition that actually happens. So this is how this entire thing actually works. This requires substantially less power to begin with. All right, so this is good. So mostly for PIV, you will use solid state lasers. So solid state laser materials are generally pumped by electromagnetic radiation. Semiconductor lasers are done by electric current, and gas lasers are done by collision of atoms or molecules with electrons and ions. So this is the way that these lasers are pumped. Okay, because you need pumping energy, right, to make the electrons go to that higher energy level to create that inversion. So as a consequence of this population inversion, what happens is that the pump mechanism, spontaneous emission occurs in all directions, which basically causes excitation of the neighboring atoms. So this initiates a rapid increase of stimulated emission and therefore radiation in a chain reaction. So this is how this thing actually happens. All right. So in case, if you look at a laser material, it is of cylindrical shape. Okay. So the rapid increase of radiation occurs in a defined direction. Okay. Because the amplification increases with increasing the length of the laser material. So you have an optical resonator, which is a mirror arrangement for the laser material to form an oscillator. The simplest way is to do this, that you have two exactly aligned mirror. A photon, what happens is that it impinges on one of the mirror, is reflected, and then it is amplified in the laser material. This process is repeated so that you see more and more photons basically comes out. It increases as we go on increasing the number of reflections, because more and more photons will be knocked off from the material, from the laser material, and therefore it will generate what we call a stationary process at the stationary process. So in other words, what we will do along the resonator length, you will form this standing waves, which has got basically, as you can see over here, this is L is equal to m lambda by 2n. So n is the refractive index, m is an integer number, and L is the length of the resonator. Okay, so the frequency according to the transition does not correspond to exactly one wavelength, but rather to a spectrum of certain band. This we already covered during the laser. Okay, because this depends also on the short transition time that you have for these two processes. Okay, in addition to this, the lasers will have different cross sections. These are the different transverse modes of the laser. So this is a cross section of the laser beam that can be divided into several ranges. This is TEM00, okay, and then you can go higher and higher. Okay, so these are the cross section of the laser beam that happens. This is because of oscillation of out of phase oscillations. That's what this actually. This is why this actually happens. Okay, so the working principles of an Nd:YAG laser, you will see that there is a flash lamp, and this is the Nd:YAG rod. Okay, and these are mirrors. Okay, you can have a second harmonic generator, and this is the pumping chamber. Okay, and this is a Q switch. So the laser material basically consists of, this is an infrared laser, as we know, it is 1064 nanometer, and the second harmonic is at 532 nanometer, it is green. So these are the most important, solid state lasers. This is Nd:YAG. So it is neodymium YAG laser. So its Nd3 plus ions are basically generates the beam. So these ions are incorporated into various host materials. The YAG crystals in these cases are commonly used. So these have got very high amplification. That's why they make for good candidates, and they have good thermal and mechanical properties. So how do you do that? The excitation is achieved by optical pumping in the broad energy bands and non-radiative transitions into the upper energy level. It's a 4-level laser system. So solid state lasers, as we know, can be pumped with white light because of the arrangement of the atoms in the lattice. Okay, so this is a long story. We need not consider all aspects of it, but one can say that the upper energy levels of this system are not very discrete, but they are more continuous. So this allows us to have a white light excitation source. Okay, so this this is different from the energy bands that is formed by single atoms. The Nd:YAG is a 4-level laser system, and it has got a very low threshold to start the stimulated emission. So you can get all those things. The basic arrangement is still the same. There's a flash lamp, there are 2 mirrors assembly, and there is an optical resonator. Therefore, then there is a second harmonic, and then you get a green light out of it. One uses the 1064 as well, but that is invisible to our naked eye. Okay, so so the pumping source excites the laser material by introduction of electromagnetical or chemical energy. Okay, so that is how this lasing actually happens. So if you now look at the different aspects of the laser, so this is, for example, a double oscillator system, because in PIV you need 2 pulses, remember, which are well separated by a certain separation distance. So these are more into the complexities of the whole thing, that this is the double oscillator laser with critical resonators. Okay, and then there is the beam alignment happens. Beam alignment behind the frequency doubling, which basically converts it to 532. Okay, so this is the arrangement that is actually shown. This is the output beam. This is the 532 nanometer beam shutter. So if you open up a laser, you will see all these things. Okay, so there is the crystal doubler. Okay, which basically creates and there is a phase angle adjustment, which you will see shortly what that actually does. So this is the pump cavity. Basically, these are the Pockels cells, and this is the variable reflectivity mirror. Okay, and then you have the crystal doubler, and then you have the polarizer, and then you have the dichroic mirrors, and then you have an output beam. So some of the properties of the modern Nd:YAG systems, you can have rep rates. I mean, these are low speed PIV lasers which can go up to 10 hertz. ND-YLF lasers actually go up to kilohertz order. Okay, so then there is a roundness of the beam, 8 meter from the laser output and 0.5 meter from the laser output. Then there is a spatial intensity, the line width. The line width, remember, this is not one frequency, contrary to popular belief, but it is still very narrow, the laser line width. Then there is a beam pointing stability also. Then there is a divergence, because the light actually diverges a little bit. Then there is jitter between 2 laser pulses. Okay, then there is delay. The delay can be anywhere between 0 to 10 milliseconds. We can adjust the delays. The lasing duration is usually of the order of nanoseconds. And the working temperature is within the room temperature, generally not in a very hot environment. Okay, so this is kind of the kind of laser. So all the beams you can see comes through the same hole. So in other words, there are not 2 separate holes. So you use the same beam alignment optics for doing this double oscillator laser system. Okay. So what is a second harmonic oscillator, second harmonic generator? That is basically, is a nonlinear crystal. It's a nonlinear crystal used for frequency doubling of the Nd:YAG laser emission. So what it does is that it converts the infrared light into the visible green. Okay, so how does it happen? The process of this frequency doubling takes place when the crystal is oriented in the direction of the propagation of the pump beam. Okay, so that the direction of the propagation of the pump beam is at a particular angle with respect to the crystal axis. Okay, so because this is a nonlinear crystal, and this condition is called phase matching. So therefore, the crystal can be usually angle tuned by the user. So you can actually do the crystal tuning yourself. If you would have opened it, then you can see those crystals. the refractive index, and therefore the actual phase matching varies with temperature also a little bit, because the crystal has to be temperature stabilized. Okay. The prism harmonic separator can be used to separate the second harmonic by deflecting it into an energy dump. Okay. The two energy dumps are therefore provided. Okay. Two energy dumps are actually provided. Okay. And, one for the fundamental and one for the third harmonic. So these separators are, so you basically separate out the second harmonic because you don't want the 1064, and you do not definitely want the third harmonic. Third harmonic is also useful for, for acetone pliff and stuff like that. But the separators, these separators are essential when you are actually dealing with the lasers. Okay. So so this is an important statement that we are actually making over here. So now let us look at when you actually do light sheet optics. Okay, so we can also have white light sources and light delivery, but light sheet optics is what we wanted to do. So the essential element for doing PIV is the generation of a light sheet, right? So the essential element for this is a cylindrical lens. So when using lasers with sufficiently small beam diameter and divergence, like argon ion lasers, for example, so one cylindrical lens can be sufficient to generate a light sheet. But for Nd:YAG lasers, you need combination of different lenses. At least one additional lens has to be used. Okay. So if you look at the configuration over here, okay, there is a third cylindrical lens as well. Okay. So there is a third cylindrical lens also that you can see to generate a light sheet of a constant height. Okay. So now the combination of a cylindrical lens together with two spherical lenses act as a telescope. Okay. That makes the system very versatile. So this is what is shown in this particular figure. Remember, this is from Marcus Raphael's book. Raphael's book, because so here you use basically two spherical lenses to make the system more versatile. Okay, so the height of the sheet is shown over here. Okay, and the height of the sheet, and it is mainly given by the focal length of the cylindrical lens in the middle. Okay, in the middle, the cylindrical lens in the middle. A diverging lens, that is a negative focal length lens, could also be used in these cases to open up. Okay, and this adaptation of this light sheet height can be and has to be done by replacing the cylindrical lens with another cylindrical lens. Okay, so this is how these things operate. So you can also see the evolution of the light sheet profile with different optics. This is, for example, light sheet optics using cylindrical lenses. And these are some of the recommended ones. This is the non-recommended ones. For example, the proper orientation of the lenses are shown over here in these cases. This configurations, this and this are recommended because they reduce unwanted reflections, and also, spherical aberrations are also kind of curtailed. This is what happens. Okay. Now we take a little bit of a look about the imaging of small particles. You know that we have already done it in our diffraction lecture. So what happens is that when you actually have light waves which is hitting an opaque screen which contains a small circular aperture, it can be a particle also, they generate a far field diffraction pattern on a distant observing screen. This we already have seen about the airy disks. Okay, so what happens is that the image that it casts on the screen can be imaged on a camera. So the image of a distant point source, example, a small scattering particle inside a light sheet, does not therefore appear as a point. Okay, it appears but forms a diffraction pattern. Even if the lenses are completely aberration free. So ideal optics also gives rise to a diffraction pattern. So the central peak looks something like this. So for example, this is a 50 micron and this is a 100 micron. So as you can see, 50 micron is left, 100 micron is right. So a smaller particle gives rise to a wider, array disks. So the small aperture diameter, or in this case small particles, for example, correspond to large array disks. Okay, whereas the bigger particles corresponds to smaller array disks. Okay, so the central peak is basically the central peak of the distribution is called array disk, and the rings that are around it, and these are called the Airy rings. Okay, so the Airy function represents an impulse response. This is a spread function of an aberration free lens, and if you do a little bit of a math, you will find that this can be represented by a first order Bessel function. So the value of the radius of the ring, and therefore the array disk for a given aperture diameter dA and wavelength lambda, is given by this. So the rule of thumb is that smaller the particle, more is the size of the array disk. Okay, so this we already know from our previous experience. Now, if we imagine that we are imaging objects in air, the same media on both sides of the lens, etc., etc., this is a geometric optics. This is an object plane. This is the image plane that you can see. Z0 is the distance from the image plane, and the lens, and capital Z0 is the distance between the lens and the object plane. So you know the magnification already, which is given as small z0 divided by capital Z0. So the following formula, this you have also seen for diffraction limited minimum image diameter, is this. So f number is of the lens, which is, the f stop is defined as a ratio of the focal length of the lens, okay, and the aperture, which is dA. So aperture, this we already have covered in quite a bit of details, and m is the magnification, lambda is a wavelength. So the diffraction, limited minimum image diameter comes out to be something like this. So in this case, in PIV, this will be obtained when recording small particles of the order of a few microns at small magnifications. Okay, for larger particles, okay, and larger magnifications, the geometric imaging becomes more and more dominant. But this is the minimum image diameter that you are going to get. So this poses that if we do not have any lens aberrations, for example, and the point spread function can be approximated by the Airy function, then the following, formula can be used, which is d tau is equal to this, where m dp square plus d diff square, when the size of the particle's geometric image, which is mdp, is dp is in the subscript, is considerably small. So if this is considerably smaller than df, then the expression is dominated by diffraction. So if the particle is very small, then it is the diffraction. So your diameter simply does not change. You get this unique size, and it reaches a constant. It is constant, virtually constant. But if it is dominated by the geometric image size, then where the particle size images are considerably larger, then this becomes equal to mdp. Okay, that means larger particles are more favored. The smaller particles can be under the diffraction limits. So you can see that the diffraction limit is very, very important, because beyond a certain size, you cannot really, recognize the particle any longer. So if you go and look at it, you will see that it's very, very hard. It is a function of the wavelength, obviously. So smaller the wavelength, less is the diffraction diameter. So you can go to smaller particle sizes, essentially. This is what it means. So first, your PIV evaluation should show an error in velocity measurements because of the particle diameter. Okay, this is from the book. You can read it. So for most practical situations, the error is minimized by minimizing both the particle diameter and the uncertainty in locating the image centroid. Second is sharp and small particles are particularly essential, okay, to obtain a high particle image density. But then this carries because you need to, but then this reduced to low scatter, and this also leads to imaging problems. So smaller particles are required for PIV because they act as good tracers, but at the same time they bring this additional baggage of low scattering, that is low intensity, and this diffraction limit. All right. So the particle diameter obtained earlier can be used now to find out the depth of field for typical macroscopic PIV, and the formula is this. So this is the depth of field that you have. It is given by this. This is the diffraction, and this is the magnification. So you can be seen that a large aperture, that is a small f number, is needed to collect sufficient light. All right, a small f number is needed. That's a large aperture actually is needed to collect sufficient light from each individual particles within the light sheet and to get those sharp images. Unfortunately, a large aperture also leads to small depth of field because it's a small f number. Large aperture leads to small focal depth. This we have already seen in our previous lectures. This is a significant problem when you try to, image small tracer particles which may go out of the depth of field quite easily. So these are problems, okay? These are problems, and this is what you need to address, okay? So therefore, these are the problems that one needs to figure out, okay, before you actually choose your tracer, choose your light source, choose what kind of a depth of field you should be using, so long and so forth, right? So in the next class, we will look at also a little bit about perspective projections, okay, and see how that actually, is affects the PIV.